Hi. So today is all about the mempool, and so I'd like to talk about how we build a counter abstraction and why the mempool has to be so damn complex. First, in order to understand the counter abstraction mempool, we need to understand what is really a user account. And one way to look at a user account is the entity that represents the user on chain and doesn't require any intermediaries. And an EOA satisfies this requirement. An EOA is definitely a user account, meaning the user can sign you sign a transaction with your private key, you propagate it, it gets included. You don't depend on anyone. Now, a smart account doesn't satisfy this requirement. A smart account needs the help of an EOA to submit the transaction on its behalf, and this means that the transaction is actually signed twice, once for the smart account and once for the EOA that pays for the gas. This is of course not sustainable. It's not a good UX. It's a terrible UX. And we can't have it, we're not going to be able to bring the next billion users if we need them to sign each transaction twice and to maintain an ETH balance in another EOA just in order to use their account. So this needs a solution. The naive solution, of course, there's the centralized approach, which is let's use meta transactions. Basically, the idea is that instead of the user signing the EOA transaction, let's have a relay server that has a funded EOA. The user signs the smart account call, sends it to the relay. The relay takes this call, wraps it in a transaction which is called meta transaction. This meta transaction pays for the gas and gets on chain, and then this finally gets, so when it gets to the user's smart account, the smart account peels off the outer layer and makes the call and compensates the relay, pays the relay to make the call. So this approach works, but it's centralized, which means that we lose some properties that we expect from the blockchain. Like what happens if the company that runs the server goes bust? They stop paying their AWS bill, and one day you try to transact with your account and the relay is not responding. So now you can't transact with your account the usual way. It's not that you are blocked. You can use an EOA to transact with it, but most users wouldn't know what to do at this point. So the account is not accessible. Or maybe the company is alive, but the server is not because it's being attacked. It's one server or a small number of servers, so it's being DDoSed, and suddenly you can't access your account. And of course, this will happen at the worst possible time. Or maybe it's alive, but it's extracting MEV in a harmful way, front running all of your transactions. And you're not going to be able to do anything about it because the server is actually the one sending the transaction on your behalf. So they're in full control, you're not in control. Or it could just censor some of your transactions, not let you do certain things, or share information about your transaction. It knows your IP address and your transactions, so it can associate your on-chain activity with your identity and share this information with anyone. So how do we solve this? One approach is the naive solution. Let's run many servers. What if the wallet company runs multiple servers? So that obviously doesn't solve anything because these servers are going to censor together or they're going to die together. The next logical step would be, let's make it a decentralized and incentivized network of relays. And that's exactly what we did with GSN, with the gas station network, which we built many years ago. So we can have a network of independent relays that not necessarily behave the same way and go down together. But there's a catch. Like, what happens if the account behaves in an inconsistent way? So the account appears to be compensating the relay, which needs to be compensated for its services, otherwise it's griefed and it will go down. So it appears to be compensating, but then on chain it decides, actually, no, I decided not to pay for the transaction. And so the transaction happens, but the relay doesn't get paid. So that's a problem. Now we start thinking about how could we solve this problem? Like, can't the relay, what if the relay knows about the account implementations, and it will only serve account implementations that are known to be safe and not to try to grief it? That would work to some extent, but it means that someone has to decide which accounts to whitelist, like which account implementations are valid and the rest are not, and that means permissioned innovation. So that's not what we want. We want to have it fully permissionless. So another thing the relay could do is to whitelist users. Let's say you require the user to open an account, to fill a CAPTCHA, whatever, and sign in. And now you can start rejecting the user if the user griefs the relay stops serving it. The problem again is that if they are allowed to censor you because you are misbehaving, then they can also censor you for other reasons. So we lose censorship resistance again. Now, what if the relay instead keeps a reputation per smart account, and it rejects account that try to grief it once? That doesn't work because of Sybil. Because anyone can deploy any number of accounts. So then it gets complicated. What if the relay simulates the transaction? So it will simulate the transaction, it will check that it's paying, and then it will submit the transaction through a Flashbot relay. Tell the Flashbot relay, please only include this transaction if it pays me. So this will initially work, but then when someone decides to grief the relay, and it starts sending transactions that behave inconsistently, trying to not pay on-chain, these transactions will get dropped by the Flashbot relay after simulating them. And the attacker can keep sending these transactions, which cause a lot of work to the Flashbot relay, until Flashbot decide to block the relay, so the relay itself is no longer able to send any transactions. And we're back to square one. We have all the transactions are being censored because the relay is no longer accepted by Flashbot. So we could go on and on, but it's clear that without a structured approach that considers all of these risks, it's not possible to have a robust and censorship-resistant solution. Either it's not going to be robust and we're not going to have a network, or we're going to have a permissioned network. But if we do solve it, we end up with a network that is permissionless and can serve any account. So ERC-457 is all about solving this problem. How does it do so? So the focus of ERC-457 is to have a fully decentralized account abstraction. We want to abstract everything about the account without compromising on decentralization or censorship resistance. It means that there are no centralized components and nothing is permissioned in the system. And since the account is fully abstracted, there are many ways in which it could attack. It could, for example, invalidate previously valid transactions. So we need to address a lot of attack vectors. Let's take a look at some. First, in order to solve the problem, we need to have certain properties. Like anyone should be able to spin up a bundler and serve user operations, but they should not be able to mess with these operations. And any user should be able to propagate a user operation to the mempool, but no one should be able to censor it. We need to make sure that the bundlers get paid for their services, that they can be profitable, and we need to make sure that they cannot be griefed, that they cannot lose money based on something that the user does. Otherwise, they will not be able to keep operating. And of course, protect the entire network from denial of service attacks. So in order to achieve this, the first thing we needed to do is to separate we need to separate validation from execution. So that validation, so it's clear which part of the user operation is validation, which consists of, the validation could be potentially unpaid work for the bundler, because if it's not valid, it cannot be included, it's not going to be paid. And then there's the rest of the transaction, which is called the execution. So once we separate it, we can do things such as separate gas limit. We can say it doesn't matter if the transaction is a 5 million gas transaction, we are limiting the amount of work that it can require during validation to a smaller number. And this way, it cannot cause too much, like a single transaction can only cause so much work. Now, we still need to make sure that the transaction, that no one can send us a large number of transactions, that each of them requires a small amount of work, but together they require a lot of work. So what we need, one property we need to satisfy is that if a transaction was valid when it was processed, propagated through the mempool, it needs to, with high likelihood, remain valid. We need most of the transactions that were valid to also be valid at the time of inclusion. It's okay if some of them are not, but it can't be it can be a lot of them. So, for example, suppose we had an account that that during validation checks the block number, and this account accepts transactions during even blocks, but rejects them in odd blocks. And now we have an attacker who sends many transactions from such account, sends a very large number of transactions during an even block. So they all get propagated through the mempool because they are currently valid. But then in the next block, when they are put in a bundle, this bundle is actually not valid because now it's an odd block number, so they have to be dropped. This would obviously cause a denial of service attack against the network. So we needed to prevent access to certain opcodes during validation. Now, of course, during execution, you can do whatever you like. You can call anything. But during validation, you don't really need to be able to look at the block number or difficulty, random, whatever. You don't need to look at that in order to validate the signature. So in validation, focus on validating. Don't use these opcodes. If you use them, the transaction is not going to be considered valid by the network and it will not get propagated. Another form of mass invalidation, of a way to invalidate a large number of transactions, would be to use a flag. Let's say we have a singleton contract with a flag, and we have accounts that require this flag to be 0. So now someone can send a very large number of transactions, and then front run all of them with a single transaction that does one S-store and changes the flag to 1. At that point, all of the transactions were invalidated, and the cost to the attacker was just 1 S-store. So it cost the attacker something, but it's order of 1, and the work that it caused is order of n. And the attacker could repeatedly do it, and at the cost of a single slot write, could keep invalidating and could keep the entire mempool busy. So we limited the storage access during validation to only the account storage or storage associated with the account, which like a mapping of this account in a third-party contract. This way, two accounts cannot look at the same flag, and this increases the cost of the attack. Now, if an attacker wants to invalidate n transactions, they have to actually write to n slots, and this becomes too expensive, so the attack doesn't scale. So another problem would be that if a transaction is valid during if it's valid when it is tested alone, but then it's invalid when it's running in a bundle, then it could invalidate bundle, and then it becomes really hard for a bundler to construct a bundle. It will do a lot of work trying to mix and match transactions that don't work. How could this happen? You could have, for example, one transaction that does validation. It doesn't violate any rules in validation, but then in execution, when it can do anything, it writes to a flag. When it writes to a flag associated with the next transaction's validation. So now the next transaction validation that used to be valid before is now invalid. To prevent that, we need to perform all the validations before any execution. This mitigates any form of such attack. At the beginning of the bundle, all of the transactions are considered valid, they are all validated, they all pay. And then during execution, even if they end up invalidating each other, if they invalidate each other's execution, it doesn't matter, they're already paying for it. Then we have global entities in the system. For example, paymasters. This is the most well-known one. And a paymaster runs in the context of multiple accounts, and it can appear multiple times inside the same bundle. And in some cases, paymasters wish to access their own storage. If a paymaster does that, then it could have a flag in its own storage to detect that it's running in a bundle. For example, it will change the flag. It will change the flag during validation, and then in the next validation, check if the flag has changed. And this way, it could detect on-chain execution and cause mass invalidation again. So, in order to prevent that, we need a reputation. We need entities such as paymasters to have a way that if they do it too much, if their inclusion ratio drops too low, we need to start throttling them so they don't attack the network, so they don't cause mass invalidation. And reputation can only work if you are Sybil resistant. Otherwise, anyone can keep spinning up more, deploying more and more paymasters that do this. What we did is we added a stake requirement for entities that require global storage access. They can stake, so they have to stake an amount. This stake is not slashable. It's not slashable. They can never lose this money, but it is time locked. So if they want to get this money back, they need to unstake and start a delay. And there's a delay. It means that if an attacker wants to deploy many paymasters to run such attack, then they need to lock a very large amount of money. And this would also be infeasible to have enough paymasters locking a stake in order to perform and sustain an attack. It's going to be prohibitively expensive. Another thing we need to do is to keep track of shared resources. For example, the paymaster pays the gas for the transaction. But what happens if we have users who are if we have a paymaster that only has enough funds to pay for one transaction, but now we get 1,000 transactions sent using this paymaster, and each of these transactions is considered valid at the time of propagation, because at the time of propagation the paymaster has the funds. Once the first one is included in a bundle, all the others cannot be included because the paymaster now doesn't have sufficient funds. And since nobody is going to fund it because it's an attack, it means that all of the others have to be dropped. So it means that we need to keep track of things like paymaster balance and only drop and only allow so many transactions in the mempool according to these funds. So we could go on and on. There are many attacks, and we spent a lot of time thinking through them and finding a way to mitigate them. But why do we need all that? I mean, why do we need the bundles to apply restrictions? So in order to apply these, we can't use a Web 2 class of attack mitigation because it's a decentralized system. We can't have API keys. It's a peer-to-peer network. So in a peer-to-peer network, we need to solve the problem in a peer-to-peer way, which requires rules. But then the next question that comes to mind is, why do we need all the bundles to implement exactly the same restrictions? I mean, one could come up with slightly different rules or implement them in a slightly different way, and they would still be DOS resistant. There could potentially be more than one set of rules that prevent the attacks. The problem here lies with the spam resistance of the peer-to-peer network. If in a peer-to-peer network, anyone can spin up a node. It's permissionless, and they can start sending invalid transactions to its neighbors. It will not get propagated because its neighbors will simulate and drop them, seeing that they are invalid, but it can cause all its neighbors to do a lot of work. And this spam attack could also take down the network. What we do is in each of the bundlers, when it receives something from a neighbor, if the neighbor says this is a valid operation, and it actually turns out to be invalid, we say there is no legitimate reason for this, and therefore I'm considering the sending bundler to be a spammer, and I'm going to block it. I'm not going to listen to further operations that come from it. So what will happen is if they implement the rules a bit differently, then it means that there is at least like one possible transaction that is there can be a transaction that is valid on one of them and invalid on another. So someone will propagate such transactions, causing bundlers to start treating each other as spammers and blocking each other, which means that the mempool becomes fragmented. We're going to end up with many small mempools instead of one large mempool. And why is that bad? If we end up with multiple different mempools for different implementations, for different bundlers, first of all, it's more centralized. It means that these mempools are much more likely to censor. It's instead of having your user operation in a big mempool where someone is going to fulfill your request, there's only a small number now which could censor you. We also lose the benefit of being a multi-client architecture similar to Ethereum, because we have many different bundlers implemented in different programming languages, and it's quite unlikely that the same bug will appear in multiple implementations, which means that a software bug in a bundler is unlikely to take the entire mempool down. But if the implementations are different and they end up being separate mempools, it means that a bug in one of these implementations takes one of the mempools down, and now users are not served anymore if they are talking to one of these bundlers. And of course, we lose economic security because it means that every bundler sees only a small subset of the entire mempool, so it doesn't construct as profitable bundles as it could have. And if there is less, there is less traffic for them to include, there are going to be less bundlers. To prevent this fragmentation, we need to have multiple implementations, which we already do, but they must be compatible. They must all run the same. They must all have the same rules implemented in the same way. And in Ethereum, we needed to solve the same problem exactly. Ethereum has multiple clients. But if they were not compatible, then exactly, we would have consensus failures, which would be pretty bad. It means that we would keep having forks in the chain. So in Ethereum, it's solved by having very clear specs, which are called the yellow paper. We have a reference implementation for the EVM. We have a test suite that tests. We have like Hive test. We have tests that ensure that all the clients behave the same way where it matters, and we use things like fuzzing to catch this. And in ERC 4337, we took the same approach. You could look at 4337 and the accompanying 7562. That's where the rules are now defined. You could look at it as the yellow paper of account abstraction, and then we have. We are maintaining, the account abstraction team are maintaining a reference bundler and a test suite that allows any bundler to check and make sure that it behaves according to the same rules. And once we have the mempool live, we should be able to also run fuzzing in order to try to catch bugs, such bugs and eliminate them, so that the mempool cannot become fragmented. In some cases, there could be situations where we want to make an exception to the rule. Maybe we want to say we have a contract that we audited, we made sure that it actually cannot be used to attack the network, but it does something that is not according to the rules. So we needed a way to allow that in some situations, although it should be used sparingly in my opinion. But in order to do that, we said that there could be alt mempools. It's a bit of a misnomer because it's not separate mempools. It's still the same peer-to-peer network. It's still the same peer-to-peer network, but it has a different ID. And then bundlers that choose to implement it, choose to join this alt mempool in addition to the canonical one, can also listen and propagate to messages with this ID, which allows them to be a part of this alt mempool in addition to the canonical one. And all of these exceptions are also, we keep a reputation for them, so they can be throttled. This way, it allows us to experiment with alt mempools easily. If someone sets up an alt mempool, some bundlers joining it, and then it turns out that the exception actually was risky and someone exploited it to DOS the network, then this rule will get throttled, which means that this alt mempool gets throttled, but it doesn't affect the canonical mempool or any other alt mempools because the bundlers can keep doing their work after throttling this rule. So in conclusion, account abstraction could be really easy if you don't care about censorship resistance. If you don't care about centralizing access, it's easy, but once you start caring about it, it becomes complex, which is very much like the blockchain. If Ethereum didn't need to be censorship resistant, it would have been much simpler. The protocol is complex precisely because it addresses all of these problems. So if you're building a smart account, you shouldn't care about all this because you should care about building a great account, serving your users, giving them great features. But you can use an SDK that uses ERC4337 and then it handles this for you. So you should just choose an SDK that handles for you and not worry about decentralization. And this decentralization actually is offered to you by bundlers, but only if you are using a bundler that is compatible with the others, so it can participate with the mempool the right way. So you should choose a bundler from the bundlers list. The bundlers list where all of the bundlers in this list pass the test. You can make sure that they do, and then you can choose them.